This is topic 15-5, Applications of Quadratic Functions, Day 1. Our central question today is how can I apply my knowledge of quadratic functions to the real-world situations? Our bell work today is the Making Connections number 11 worksheet. We're going to complete the bottom half. You should also have out all your topics up until this point in addition to assignment number 15-4, and so that you can check it. So here's the Making the Connections. It's reviewing our linear functions. We want to graph the line that goes through the point -3, 2. So -3 is our x-coordinate, 2 is our y-coordinate. We'll go -3 on the x, +2 on the y, and here's our point. And then it moves, or it has a slope of 2/3. It's a positive slope, so that means I should have an increasing line. This means the top number tells you how far to go up, bottom number tells you how far to go to the right. So we're going to go up 2 and to the right 3. Up 2 to the right 3, up 2 to the right 3, up 2 to the right 3. Getting our points throughout the entire graph. We'll start at the point we begin with again, and now we'll go down 2 to the left 3 to get what the other side looks like. So we're doing the exact opposite of what we did on the other side. Connect the dots, and we do have an increasing line with a positive slope of 2/3 that does go through the point -3, 2. Now we want to graph the line y equals -2x minus 6. This is in slope-intercept form of mx plus b. So this tells you your slope is -2/1, and your beginning is at -6, or the y-intercept of 0, -6. So starting off at the y-intercept of 0, -6, the slope is negative, so this means we're going to go down 2 and to the right 1. So down 2 to the right 1, down 2 to the right 1. I've gone all the way on the right side. Let's do the left side by doing the opposite. Up 2 to the left 1, up 2 to the left 1. And again, we'll go throughout the entire grid, plotting our points before we draw our line. Now as we draw our line, we see it is decreasing, which means it has a negative slope. And we have completed the making the connections. The following are your answers to 15-4. You may pause the video in order to check your answers. So today we're going to apply our knowledge of quadratic functions to real-world situations. Our first problem is we have a rancher that has 100 meters of fencing with which to build a rectangular corral. So here we have a picture of a rectangular corral. The graph below shows the relationship between the area and the length of the corral. So this 100-meter fencing is what's used in order to build this. The area is what's inside, and so our graph represents how much area we have inside this fence to the length of the corral itself. So the length is just one side. We have a length and a width. We're going to deal with the length. So length in meters, that's on our x-coordinate. Area in square meters is on our y-coordinate. You see a nice parabola going up. It does have a maximum point. And now we're going to look. The independent variable, our independent variable are our x variables. And so our independent variable represents the length of the corral, and it is in meters. The dependent variable, dependent is our y, and so that is our area, which is in meters squared or squared meters. C is asking identify the x-intercepts. Again, we're talking about x, and then intercept means where it crosses the x-axis. So we have 2 points. Our x-intercepts are at 0, 0, and also 50, 0. When we talk about the x-intercepts, the x value is a number, but the y value is always 0 when it comes to our ordered pairs. Does this graph have a maximum or a minimum? Since it has a peak, it has a maximum. What is the vertex of this graph? Well, we can read from the graph itself. If I'm looking at the maximum, the x-coordinate is 25, and the y-coordinate is, well, it's a little over 600. So let's look at the scale. We have 1, 2, 3, 4 between there. So this would be 625, 650, 675, 700. So this would be 625. So how does the x value and the y value of the vertex relate to this scenario? So previously, I changed pictures, so I'm going to write it up here. Our vertex was 25, 6, 25, but our x-coordinate represents the meters or length, and the y-coordinate represents the area. And so when we are at our vertex, this shows the maximum area. It's the maximum area we could have because it is a maximum and a maximum length. Or let me rephrase that. This is the maximum length we can have for the maximum area. Let's do it that way. Maximum length to get the maximum area. Find the possible dimensions of the corral if the area is 525 meters. So 525 meters is square meters. No, it should say meters squared. Let's correct that because we're talking about area. If the area is 525 square meters or meters squared, so here's 525. That is a y value. So our y value is 525. We are going to go over and see where does that hit our parabola. So I have it hitting the parabola here and hitting the parabola here. Now we'll find those x values. So one of the x values is 15. The other x value is 35. So possible dimensions when y is 525, x is 15, or x is 35. So we want possible dimensions. This tells you our length. So if our length is 15, question is what is our width in order to get an area of 525? Area is length times width. If I have 525, my length is 15. We need to solve for W. We'll divide both sides by 15, and we get that the width comes out to be 35. So our dimensions are 15, 35. 15 by 35 meters. In order to get an area of 525. Some of you may say, hey, that's the exact same. You always need to check. May not always come out to be that way, that the two numbers you come up with are the ones that multiply to give you the area that we're looking for. Problem number 2, we have 3 rockets were launched at the same time. Each person in the group chooses one rocket. Answer the following questions for rocket number 3. So from what height was your rocket launched? That means what is the initial height? In other words, we don't start the rocket off on the ground, and so our height is 10 meters. Height is our y value. What we're finding is our y-intercept. When did the rocket hit the ground? Let's look. It launches, goes up, comes back down, hits the ground right here, and it's asking when. This is a time. And so we can say we know it's somewhere between 3.75 seconds and 4 seconds. If we look, here's 3.5, this is 3.75, and this is 4. It's somewhere between there. When did it hit its greatest height? This is another way of asking about the maximum, also known as a vertex. So we'll look at our maximum of vertex, and it wants to know the height. So the height is on the y-axis. So somewhere between 66 or 65 and 70 meters. Actually said when did it meet it, not what is the height. I'm getting ahead of myself. So when, let's come on down. When did it meet it? It is sometime between 1.75 and 2 seconds. So it reaches its maximum height between 1.75 and 2 seconds. What is its greatest height? That greatest height, that is between, again, we just saw that, 65 and 70 meters. This is talking about a y. And so we're going to approximate that at about 67 meters. How many seconds was the rocket in the air? So from the time that it lifted off to the time that it hit the ground, how many seconds? This is talking about x values. And so let's look. Number of seconds. It went from 0 to, let's see if this is 3.75. It's somewhere between 3.75 and 4 seconds. So it's almost 4 seconds in the air. And last, for approximately how many seconds was the rocket 45 meters or higher? So 45 meters or higher, we're talking about y values. To be 45 meters, let's go 45 meters on the y. And I want 45 meters or higher, so we're talking from this point, it's higher than 45, and into this point. So how many seconds is that? We're going from 0.75 seconds to 3 seconds. And so to figure out how many seconds that is, we'll do 3 seconds minus 0.75, and that'll give us 2.25 seconds. So how do we apply our knowledge of quadratic functions to real-world scenarios? We use the vertex to discover maximums. And we discovered maximum heights. We used the intercepts. So the y-intercept was used to find the initial height. We used x-intercepts to determine how long it's supposed to be an L, how long the rocket was in the air. When it came to the pin, we used our y-intercept, not our y-intercept, we used the vertex to determine the maximum area. So this first part was for the rocket, and then for the pin, we used the vertex to determine the maximum length to get the maximum area. This concludes topic 15.5.